Hi, I'm Martina. I'm a software architect at ReversingLabs. We are a security company with this enormous collection of malware and files. And I want to show you and tell you actually the story about the migration from our internally built key value store to ScyllaDB. Um, Here I mentioned this huge collection of files. What we do here is with these files, we process them with static analysis, with dynamic analysis, with different scanners. And my job here is to maintain this system that stores the metadata, that is the data about the files, the results of all this processing systems into different databases. And it indexes them in a different way, and it exposes this metadata through our APIs and feeds. This is a complex system of hundreds of microservices communicating in different ways. Today, what I'd like to do is first go through ReversingLabs beginnings and growth, just to explain myself and ReversingLabs here, how we got to this point of this migration, how the ReversingLabs history, how is it that we end up with this internal key value store, and how we got to ScyllaDB, and a bit of context for the migration itself. Then I'd like to talk about the migration and lead you through a couple of different steps we took to migrate all our services and all our databases. So we'll go through that. I need to tell you, I was at the time when we did this migration, I was a backend engineer. So I was very involved in this project, and it was, now I need to take a step back and show you this from a bird's eye view, and we'll go through very simplified version of this whole project, this enormous project. So at the end, I want to touch upon this distributed locking problem, which is a very interesting problem. I had very much fun working on this, but it's a complex problem, and I'll just, I don't think we'll have time to go through the whole solution, but I'll point you to resources where you can find the detailed explanation. But I'll give away the punchline at the end about this whole distributed locking thing. So now let me just give you some numbers so you can have an idea about this project, what happened, how big was actually this migration that took place 3 years ago. So we have around 20 billion classified samples in ReversingLabs. So when we process these samples with different services, gather all the reports, we then classify those samples. So around 20 billion, that is the number of classified sample in ReversingLabs data set. Around 300 terabytes of metadata, that is that data about the samples, the files that we have in our collection, mostly malware samples. Because we are a security company, our job is to classify at the end these samples and notify if something is odd or malicious. So 300 terabytes of metadata, that is from the data from 3 years ago. So now the collection is even larger. We have around 400 microservices, and that is not instances. These are actually different microservices. So each of which has multiple instances. So it's a huge system, complex system, a lot of service communication, and a lot of maintenance. So now I wanna go back to 2011. So that was 13 years ago. So 2011, in a sense of, in a context of databases, it was a time where NoSQL databases started to get popularity. That was a couple of years after the famous Big Table Google's article was published. And at the time, we had Cassandra developed internally at Facebook with version 0.6. At the time, it lacked row level isolation in 2011. MongoDB 1.6 version. Mongo had consistency issues between replicas at the time and couplets version later also. And DynamoDB was not released yet, so very limited market. Postgre, ReversingLabs was using Postgre at the time, so Postgre was okay for scalability for some time, but in 2011 we started to notice a lot of problems with Postgre, mainly because of the multi-version concurrency control that brought a lot of overhead with it. So we had mostly that is write amplification that was an issue for us, and it used so much memory. And for a startup with limited resources, of course, we had this database that eats all our memory. It was a problem. So we built our own data store. I know it's scandalous. It's a crazy idea for today. It would be a crazy idea, but for 2011, in this context, in this market, it made more sense. And we did it. We built this, not we as ReversingLabs, not me, I wasn't in the development team, but ReversingLabs built a key value store, very simple. It covered just our use case, so it was just built for us and no one else. You had to do all the maintenance manually. It was built just for the specialized database team who knew how to handle it. And it had very little features, but it worked really fast and really well. And it used really so little resources. And that was important for us as a small startup. And at the time, it enabled ReversingLabs to really stand out as this very small startup with this ridiculous amount of data. So one of the comments on my blog post said, you don't often hear we build our own database success story. I mean, for the companies that database is not its main business. So, but for ReversingLabs, it was a success. And it wasn't until 10 years later that we hit the wall. So the risk of maintaining our own database grew too big, and the number of use cases started to overwhelm the database team because the company grew. We had lots of different teams, lots of customers with all of this new interesting use cases, and our database team was too small and overwhelmed with all this. So we just had to find something else. So what we did then is lots of POCs, so a vast search, and we found Scylla to be the most suitable replacement for our existing database. It was fast, it was resilient, and it was scalable enough for our use case. Additionally, it had all those features that we were missing in our old database. So Scylla it was decided, and we started with this big migration project. So the big migration started. 300 terabytes of data, as I said, around 100 of different tables, 400 services, reading the data, writing the data, reading and writing the data, pulling from the queues, pushing to the queues, reading, writing, pulling, pushing. So a complex, very complex system that has to be migrated to a new database, main database that would serve as a source of truth. So the motto of our this big migration and the guideline, the main guideline for the team was to keep it simple. So we changed the models as little as possible. We had to make some changes, but we for example, we didn't change the code at all. So the code for this 400 services, of course, if we would change the code for every service, that would take if we still wouldn't be finished with the migration. So we decided to take the interface we had for our old database and just change the code inside it. So we had this library interface library, and we just made it work with Scylla driver, and the services shouldn't know anything, and they should just be redeployed with this new version of the library and keep communicating with Scylla instead of our old database. So so that was our main goal. For the model, so we changed, we needed to make some changes in the primary key, but what didn't have to be changed was the value, because in the key value store, we had one value, which is a packed protobuf with lots of fields. And in Scylla, we had the opportunity to unpack this protobuf and have all the fields separate, and then maybe even filter by some fields and all the features that Scylla have. We could have done that, but instead we decided to first make it work like it worked before. So just get done with the migration, and then we'll talk about features and the possibilities and everything else. So we kept these protobufs and just show it like they were in Scylla now. So the differences in architecture. So our old database, I said it was very simple. It was a key value store with a single master node. So all writes had to go through the master node. And we had this bunch of data nodes with their own replicas. And Scylla, on the other hand, it has this famous ring architecture, which is leaderless, and the differences in architecture implicitly impose some differences in data structure and how the model should be built. So, for example, we had different requirements, different, perhaps better to say, like optimal partition sizes and so on. So we had to change models a bit, but we changed it as little as possible. So of course the data should be retrievable with the same input, and we should get the same output. So our API's user do not see any difference, do not see the migration happening. So first, we started with the data migration. The data migration, after the models were ready, we were ready to migrate all of the databases to Scylla cluster. So this is a simple service that writes data to a single database, and it's the owner of this database. So very simple case, and the migration will be very straightforward. So we take this service and this old database, and we stream all the updates on the old database to Kafka topic. We set up a Kafka topic for this, specifically for this single table, and we streamed the output to Kafka. After the streaming pipeline was established, we then dumped the old database and prepared a Scylla table, a Scylla database with its new configuration and structure. And after that, we loaded the data. Of course, we changed the model. What we had to do, we changed the model, and then we loaded it into Scylla. And then we set up a continuous pipeline that would it was a service that was listening to this Kafka topic for updates, and loaded the data to ScyllaDB. So after this backlog was processed, these two databases were completely in sync. So the negligible delay between the data in one database and in the old database and the Scylla. So that's pretty straightforward and simple. But take in mind, we need to do this for every of the 100 table that we had. So this times 100. And you have your data in sync. So that's the data migration. After that, it comes service migration. So service migration, first, let me show you a sketch of our system. So this is, again, a very simplified sketch, but just to introduce you to our system. So we have these master services that are actually data generators. So they are the ones that are listening to all the new reports from static analysis, from dynamic analysis, from different sources. So and these services are the one that hold the source of truth. So their database is the raw reports that needs to be processed later on. So the master services are storing the data in their own table, and then they are streaming the updates to all the interested queues. Delivery services, next in pipeline, are the one that are combining the data from different master services, and maybe populating, maybe adding some, maybe calculating something, doing something with the data, combining different inputs. And what they do is that their purpose is to store the data in a format that makes it very easy for the APIs to read the data. So this is like a CQRS principle implemented. So we have delivery services that are optimizing the data for the query key. And they store the data in their own database, and then we have APIs reading from these new databases and exposing the data to users. So the migration. First, as we said, we have already established a pipeline that syncs the data from the old database to the new one. So we can easily migrate the APIs. So one by one, we took an API and we just deployed a new version that we're reading from. We're using this new library, new interface library that's reading from ScyllaDB. And then when we establish that everything is stable. We started switching traffic to the new version of the APIs of the API, and after all the workers were migrated to Scylla, then we would continue with the next API, and then the next and the next. So APIs could be done. We could stretch this migration of the APIs. We could take time to monitor the cluster and the API latency, and we did stretch this migration to be safe and to migrate customers one by one, but without them noticing. So we had APIs on the new database without any downtime on them. So after the APIs were migrated, we had to prepare for the big migration day. So all these services before the APIs are intertwined with their communication, and they had to be migrated all at once. So at the migration day, 9 a.m., migration team, I think it was maybe 10 or 15 of us. First step was to stop the master services, so the data generators were stopped. So their input queues accumulated until the migration was finished. Notice here that the APIs were still serving traffic, so it wasn't. There were no downtime at the time there. So it's just the data in the databases was delayed. So until this migration finished, so the new data was late maybe for an hour or two until the whole services, all the services were migrated. So after we stopped the master services, we waited these queues between master services and delivery services to empty, so that the delivery service, that means that the delivery services processed all this data and they stopped writing. And then we migrated the delivery services one by one to this new database. Of course, there was no data because we stopped the master services. So we would just migrate them and hope for the best. Of course, this was all tested before, but we just migrated them and waited then for the next step, which was to migrate and start the master services. So that was this unspectacular preparation for that led to this big migration day when we moved our whole system to ScyllaDB. So the next step was to shut down the old database, because everything was now working on Scylla. It worked great. We were happy about the latencies. We had, if you remember, our old architecture had, our old database had a single master node. So we had a single point of failure. And now we have this this resiliency, this high availability, and we're very happy about it on Scylla. So one last thing left, and that was resource locking. So in the old architecture, to lock resource, when you have a single master node with all the writes going through this node, it's easy. You can just have a mutex on this master node, and locking is finished. You can tie it. Of course, you need to tie it with a connection to the database, but that's it. And now we have this leaderless architecture where there's no, at least data-wise, no difference between the nodes. So we had this simple problem of resource locking on a single node, and now we have one of the hardest problem in distributed computing, and that is distributed locking. So what we did there is we used ScyllaDB's lightweight transaction, and on top of that, we built the whole locking mechanism. So that's the solution. We worked with guys on Scylla to implement this. We went through a lot of POCs, one more successful, one less successful. But at the end, we built this distributed locking on top of Scylla. And about the details you can read about on my blogs. I don't have the time to go into deeply into this algorithm. And that's it. Thank you for joining me here, and feel free to